In this tutorial, we're going to work on solving quadratics that are described as projectile motion problems. So let's get started. You're going to need a Ti-84 calculator to do this lesson today. If you're following along in your notes, put this in the table of contents with the appropriate page number. All right, let's get started. The learning target is to calculate the maximum and zero values of a projectile motion problem using a Ti-84 calculator. You have to be able to do these three things to be successful today. You have to be able to enter a standard form equation into the y equals button. You have to be able to use the table button, the graph button, and the window setting keys. And you have to be able to calculate the maximum and zero values using the second trace feature. All right, don't be scared. You can do this. Okay, a soccer ball is kicked from the ground with an initial upward velocity of 80 feet per second. The equation h equals negative 16t squared plus 80t gives the height h of the ball after t seconds. A, find the maximum height of the ball, round to the nearest tenth. And B, how many seconds will it take for the ball to reach the ground, round to the nearest tenth? All right, I know you're freaking out right now, but I want you to pay attention just to this, okay? I know there's a lot of vocabulary going on here. Initial upward velocity, okay? I know there's a lot going on, but I really just want you to, concentrate on this image, okay? We're working with quadratics. We're going to kick a ball up into the air, and it's going to come back down. And the reason it's going to come back down is because of the force of gravity. So a lot of our problems today are all going to start like this. And it's not a coincidence, it's gravity. The force of gravity is the same no matter what you're doing and what you have. So whether you're kicking a ball or you're dropping an egg, they are all pushed on by the same force. So when we talk about feet, our coefficient here will always be a negative 16. Now, if you're talking about meters, that would be a different value. But most of our work here is done in customary units, so we're going to be using this equation a lot. Now, this kind of is that gravitational force that's pushing down, which is why it's constantly the same. This is something different. It's the speed at which something is being forced upwards. So that's called an initial upward velocity, right? So this number is going to change for us with each problem today. So let's get started. When you are reading a word problem, focus on this. Don't worry about all of the minor details just yet. Find the maximum height of the ball. So from this equation, which is different than this picture up here, okay? For this equation, we're talking about the ground, a soccer ball, right, being kicked up from the ground and then returning to the ground, right? So there's our quadratic. So hopefully you know these parts. This is the maximum, and these are the zeros, or the solutions, okay? There's always two answers to a quadratic, and sometimes one of them is irrelevant or not pertinent at this time. This is not pertinent. This is the beginning, so I know the ball is at the ground now. The question is, when will it return? So this is the zero I'm interested in. Now I know we've done some work with factoring, we've done some work with the quadratic equation, but today we're going to focus on using our calculators. So let's turn those on. All right, first thing we need to do is put this equation into our y equals button right up here. So anything that you have there now, clear it out. And even though our problem uses t for time, we're going to use the variable button on our calculator, which as you can see here has lots of variables, x, t, theta, lowercase n. And it does that for a reason, to tell you, hey, it doesn't matter what letters on your paper, use this button and we're always going to be programmed to use an x. Okay, so it doesn't matter whether this says x or whether this says t or r, it doesn't matter. On your calculator, it goes in as an x. So here we go. Remember, this is not a subtraction sign. So use your negative key. Negative 16x squared. Then we're going to add 80t. So we're going to add 80x. Now we can certainly look at that graph, and I might as well press graph here just for fun because I know half of you are doing it anyways. And what we see when it finally appears does not look like a quadratic. We're like, what is that? And the reason why is because this ball is being kicked up pretty high, and it's going, what does it say here? 80 feet per second. And guess what our calculator is showing us? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's only showing us 10, right? It's only showing us up to 10 feet. So if I really wanted to see that whole quadratic curve, I'd have to change the way this window looks, right? It's only going from -10 to +10. So if you want to, you can change the window by pressing the window button here. Let's do that together real quick. Now right now, I have my x-min at -10 and +10, and that looks okay. That's a pretty, I mean, I could certainly say, oh, I don't need to see all this over here, but I don't even really need to mess with that right now. I kind of really want to talk about my y values. So I'm going to arrow down, and I can change a whole bunch of numbers, but for the sake of time, let's focus on our y max. Well, if it's going 80 feet per second, then I know that it's going to go up pretty high. So I'm going to change this to go by, maybe I'll make it go up to like 160, see if it goes up that high. And then I'm going to do one other thing. I'm going to come down one more time to this one right here, YSCL. That's called the Y scale. Now I can have the scale go by ones, but that's a lot of lines. Let me show you what I mean. Right, so you're going to see this line here. On an older calculator, you might see really thick black marks. I could also change that so that the scale goes by tens. I could do that if I wanted. Depends on how new or old your graphing calculator is. All right, and now that I've changed my window here, you see now you can see some tick marks. I can really see that quadratic, which is nice. If you can't see the maximum of your quadratic, you need to change the window, because what I want you to calculate today can only be done if you can see the maximum. So you kind of have to use your common sense about reading this problem so that you're not making like totally random guesses here. Like if somebody came down and was like, oh, I can't see it, let me put 1,000 in here. Right, which isn't wrong, but then when you go to look at the graph, oh, that's what I was talking about before. When there's so much to see. Oh my gosh, see, it looks so tiny. Well, the good news is we can still see it. I'm going to go back here to 160 because that was an appropriate scale. All right, now let's get to the hard part. How do you calculate that maximum? Now, I know a lot of students like to press this trace button. They see their cursor appear on the screen and they start pressing these arrows and they're like, oh, okay, I'm tracing here. Oh yeah, it looks like it's at 2.42. Now, that's pretty good, but it's not exactly accurate. It's kind of jumping pixels here. So if you want to be exactly accurate, you have to use this blue calc feature. Do you see it here above the word trace? So we're going to press second, trace, which gives us our calculation menu, and we're going to choose number 4. We want to calculate the maximum. Now the calculator is going to ask you 3 questions. Are you to the left of it? Are you to the right of it? And are you ready for me to take a guess? So I need to move my cursor over a little bit. Now it doesn't need to be way down here. You want to be close, but not like on top of the actual answer. So I'm going to put my cursor right about here. Yes, I am to the left bound. Now I'm ready to press enter. Now I'm going to move my arrow to the right a little bit, and I'm going to press enter because I'm on the right. And now you see what's appeared, these long skinny lines? That's where the calculator is going to look. So I'm going to press enter. Yes, I'm ready for you to make a guess. And there's our answer. The maximum is 100 feet high at 2.5 on the x-axis. So remember, and I can go back to my paper here for a second. The ball is traveling up. This is the height. Remember what this one is? The time. So what was the maximum height of my ball? 100. What time did that occur? approximately 2.5 seconds, right? So when it asks you find the maximum height of the ball, you're going to say 100 feet. If it asked you when does that occur, then you would say it occurs at 2.5 seconds. All right? If you wrote that on your paper, it would be incomplete. You have to specifically state which of these two values represents the maximum. And the answer is that one. It occurs at 2.5 seconds, but the maximum is 100 feet. So it's important for you to recognize that. 100 feet at 2.5 seconds. All right, how many seconds will it take for the ball to reach the ground again, right? So it goes up, comes back down. This is what we're looking for, and that is called a zero. So let's turn our calculator back on. So I see my graph here. I'm still in the maximum calculation mode. I'm going to quit for a second. I'm going to go back to my, quit, go back to my graph. Now, if I want to know this value here, right, that solution, that's called a zero. So I need to press second, trace, and I need to calculate number 2, the zero. It's going to ask me the same question as before. Are you to the left of the point you want to find? So get as close as you can, but don't be on top of it. Then go to the right, which for us will kind of be below it. Press enter, and then it will look in this zone. Ah, now that's beautiful. The zero is 5. Remember, your x-intercept is always your solution. So if it asks me how many seconds will it take for the ball to reach the ground, round to nearest tenth. Now sometimes I'll have students ask me, is this the same answer? Well, technically those values are equal. But if I say round to nearest tenth, that means I want something in the tenths place, even if it's a zero. So keep that in mind. That's the right answer. All right, getting the hang of how to use this calculator? All right, next question. A golf ball is launched directly upward at 64 feet per second from an 80-foot platform. The equation for this golf ball's height h at time t seconds after launch is h equals negative 16t squared plus 64t plus 80. Find the maximum height of the golf ball, round to nearest tenth, and then how many seconds will it take for the golf ball to reach the ground, round to nearest tenth. This is exactly like what we just did. Don't worry about all that business. Concentrate on your equation. All right, turn those calculators on. Give this a try on your own. Pause the video now. All right, let's see how you did. Y equals negative 16x squared plus 64x plus 80. Now, I didn't change my settings. Let's see if they're still appropriate. This one is, oh yes, my settings are still good. I love it when that happens. All right, let's find the maximum height. Second, trace, number 4. Move your arrow to the left, as close as you can get, but not too close. Then move your arrow so it's to the right. Then press enter a third time. Ooh, 1.999. I'm going with, I'm calculating maximum, so I don't even care what the x value is. 100. At about. Right, remember the maximum is only the y value. All right, how long will it take the golf ball to reach the ground? So that's this right here. So if I was tracing it and I was moving my cursor, I would be looking right down here, right? So I can certainly guess, but I think I should use my calc feature. Second, trace, number 2. I want to calculate my 0. So move my cursor so that it is above it, which technically is left bound. I know that's weird, but I'm to the left. Now arrow over to the right, Press enter again, and it looks like 5, ooh, round to nearest 10th, right? Okay. Number 3. A water balloon is dropped from a window 25 feet above the ground. If the equation of the water balloon's pathway can be modeled by the equation h equals negative 16t squared plus 25, how long will it take the water balloon to reach the ground? Oh, I have a typo. I gotta fix that. All right. Find the maximum height of the water balloon, round to the nearest tenth, and then how many seconds will it take for the water balloon to reach the ground? Round to the nearest tenth. All right, give it a try. Get that calculator out, clear out the y equals button, and enter your equation. Pause the video now. All right, let's take a look and see how you did. You type that into your y equals button, you press second trace, you calculated the maximum, and you got y equals 25. Now, doesn't that make sense? I'm not actually throwing my water balloon up. I'm in a building, and I'm dropping it down. So wouldn't my maximum be my initial value, right? Wouldn't my maximum be my initial height? And then the water balloon is dropping down. So that makes sense that my maximum height is 25 feet, right? 25.0 feet, I guess, 25.0 feet. How many seconds will it take for the water balloon to reach the ground? Well, I didn't change my scale here. I certainly could do that. But you're going to press second, trace, and then you are going to press number 2, which is the 0 calculation. Second, trace. Oh, I think it's still graphing. You see that right there? It's still working. Oh, there we go. Second, trace, number 2. All right, left bound is above, right bound is below. Press enter again, and it looks like 1.25 seconds. 1.3. This one's a little tricky. A penny is dropped off the Empire State Building, which is 1,250 feet tall. If the penny's pathway can be modeled by the equation h equals negative 16t squared plus 1250, how long will it take to strike a 6-foot tall person? So before we wanted to know when something hit the ground. When something hits the ground, that means the height is 0. That's standard form. But if I ask you, when will it hit a 6-foot tall person? That's not standard form. You see that? Okay, so there's a difference between this and what we were doing before. So now I need to make this 0. In order to do that, subtract 6 from both sides. So you should not be putting this exact equation into your calculator. You're going to put this equation into your calculator. All right, now I think you're ready to solve this problem. Remember, I want to know when it hits this person who's 6 feet tall, and I've already substituted that value in. So now that I've taken into account, I want to know what the 0 value is. Pause the video now and give it a try. Okay, let's see how you did. You typed your equation in. I'm going to change my window here, and I'm going to make it go up to, see, I know my initial value here, the penny is dropped at 1,250 feet, so I'm going to make this go up to 1,300. And then when I graph it, I see this nice parabola here. Again, I want to know when it hits that person, which is right here. So I'm going to press second, trace, and I'm going to calculate the 0. Now again, there are 2 zeros, But this one is irrelevant, right? It does not pertain to our problem because we can't go back in time. So we want to know if I drop the penny, when will it hit here? So I'm going to move my cursor to the right. And in order for me to be right bound, I have to be off the screen, which is okay. I'm going to press enter. I'm going to click twice to the right, press enter, and then I'm going to take a look. And it looks like the 0 is 8.817. 8.817. So about 8.8 seconds later, oh gosh, please don't ever do that. If a penny hit somebody from dropping off the Empire State Building, it would cause some serious irreparable harm, possibly even death. All right. This next problem is exactly like the last one, so give this one a try on your own. Pause the video now. All right, let's see how you did. So when will the firework be 30 feet high? That's the equation you should have used. All right, so if you didn't, consider what the new equation should have been. Maybe pause the video and give it a try again. So when I typed it in my calculator, I happened to choose a window of approximately 100 feet high. And when I graphed it, I was able to see the entire parabola. And I want to find out here, right? I want to find out that solution. So second, trace, number 2, and I'm going to arrow to the left. Press enter. Arrow to the right, press enter again. And it looks like 4.59 seconds. 4.6 seconds later, those fireworks are going to land on your neighbor's roof and they'll probably be pretty mad. All right, why don't you take a look at this question and try this on your own. Pause the video now and see if you can get the question right. All right, let's take a look. The equation we're going to enter is negative 16x squared plus 110x plus 10. And I'm not sure, but my window right now of 150 wasn't enough for me to see the maximum value. So I'm going to change my maximum maybe to go up to 200. And let's see if that's a better view. Wow, it just made it. Sometimes when kids press their window button, they get some really funky numbers all over the place. Like let's say you get something like this all over the place. If that happens to you, just press zoom and then choose number 6. It will reset it back to all the defaults, negative 10 to positive 10, and it won't be so crazy on you. So if that happens to you, just choose that. For me, this seems fine. So I'm going to calculate my maximum here, second trace, number 4. I got an arrow all the way up here to the top. All right, press enter. Now go over here, press enter. And it looks like I have a maximum of 199.06. So it looks like the maximum height of El Toro is 199.1 feet, or almost 200 feet high. That's crazy. All right, let's give another one a try. Pause the video now and answer this question. Again, don't just say yes or no. Give a reason to support your yes or no answer. Okay, pause the video now. All right, let's see how you did. Enter the equation into the y equals button. Take a look at your graph. So I'm still using the settings from my last question. Let's see what I get. Oh, it's pretty tiny. I want to change that window. So instead of going all the way up to 200 feet, maybe I'll make this 80 feet. All right, let's see. Maria's definitely not going to jump as high as an 80-foot building. So maybe If she's jumping on a trampoline, I guess the question is, will she ever get to be 14 feet high? So let's make this a 20. That makes better sense, right? So let's see. That's 20 feet high up at the top of my graph. So it looks like that's about halfway. Well, it's definitely more than 10 feet high, but is it 14 feet? So let's take a look. Second trace, maximum 4, left bound, enter, couple clicks over, right bound, enter, make a guess. So 12.25. So the answer here, oh sorry, I think it was 12.25. Yeah. So I'm going to round that to nearest 10. Nope. She will not jump 14 feet high. The highest she jumps is 12.3 feet. All right, let's take a look at another question. So this is the last one we're going to work on today. And this one has to do with the metric units. So an astronaut on the moon throws a baseball upward with an initial velocity of 10 meters per second. You notice we're not having that same value here because we're talking about meters and not feet. Letting go of the baseball 2 meters above the ground. That's where the 2 comes from. And that's where 10 comes from, initial velocity. But all of that is irrelevant. It doesn't even matter what all that says. Focus on this. The same experiment is done on Earth, in which the pathway is modeled by this different equation. How much longer would the ball stay in the air on the moon compared to on the Earth? So remember, when a ball is launched, that's the amount of time it's in the air, from launch to land. So when does it hit the ground on the moon? When does it hit the ground on the Earth? And let's compare the difference in that time. Okay, pause the video, see if you can try this on your own. Okay, let's see how you did. So I typed in both of my equations. Let's just double check, whoops, that I'm getting these typings right. Negative 0.8x squared plus 10x plus 2, negative 4.9x squared plus 10x plus 2. All right, so I have a color calculator here, so I'm going to be able to see both of my graphs at the same time. One is going to be graphed in blue, and the other one is going to be graphed in red. And I still have my settings from the last problem, and it looks like I can't even see where that blue one is going to cross the x-axis. So why don't I change my window here? It looks like my x max, my right bound here should be a little bit higher. And I think even my y should be a little bit higher. Well, not much, but a bit. So I'm going to choose these settings. All right, let's see what I can see now. So this is the balloon on the moon. I'm sorry, baseball. This is the baseball on the moon. And then the red one is the baseball on Earth. So look, you see that? Wow, it stays up in the air because the gravitational force is so much less on the moon, right? So on the moon, so I'm going to calculate second trace. I'm going to calculate my 0 here. And I'm going to arrow to the right. I'm going to press enter, arrow down, press enter. So it looks like it's 12.7 seconds. So let me take that note. So I'm going to say the ball is airborne for 12.7 seconds on the moon. Now, I'm going to use my up or down arrow here. You see how the screen is changing colors? So I'm going to use my up or down arrow here. Whoops, sorry. To change to my red parabola. Now, you see this here? I'm going to press the left button. Oop. I got to get, second, trace, number 2. I got to calculate. I'm going to press my up button, and then I press my left arrow. I'm going to have to press on this left button for a long time. And whoa, there it is. till I see that cursor. Okay, again, remember I'm calculating a 0, not the maximum. So I'm going to say left bound is there, right bound is here. What's my guess? 2.22 seconds. So 12.7 seconds on the moon, 2.2 seconds on the Earth. So 12.7 minus 2.2. So how much longer would the ball stay in the air in the moon compared to the Earth? We're going to say 10.5 seconds. Addendum. It will stay in the air 10.5 seconds longer on the moon. Excuse me. And that concludes our lesson on projectile motion. All right, I hope you feel comfortable with this calculator and calculating the maximums and the zeros and all of that. So hopefully you can tackle any word problem that comes your way. All right, that's it.